Where are we? Friday we started the feasibility and stability issue. We have to complete that today. You received 3 set of slides. Is it 3 or 1? 1, and you'll see there will be 3 parts. First part is practical. We're going to cover it today. It's about extending the MPC formulation to reference tracking and soft constraints. Okay. The second part is hybrid. Third part is explicit. I hope we can cover for sure the first one and the second one today, and maybe the hybrid. Okay. So let's go back to feasibility and stability. Where is feasibility and stability? Okay. So remember, in the big picture, there are 2 main issues. First one is about computation. It takes a long time to solve this optimization problem in real time to implement an MPC algorithm. Okay? And you have had a whole lecture yesterday about how to speed up, what are the techniques to design fast solvers. Okay? The second issue was you have to remember this picture. Let's see. Let's start from slide 529. Do you remember the green and the red? There are points that start feasible and converge to the origin, but there are also points that start feasible and become infeasible. Okay? So there are 3 sets. The first one, we called it a calligraphic X. So I have to adjust, sorry, one second, I have to adjust to this thing this morning. Okay. This was our calligraphic X. We wanted to keep the state at every time instant inside -5. We have 2 states, X1 and X2. We always want to be within this box. Okay, this was the design in the MPC problem, calligraphic X. Okay. Once you solve the MPC problem, okay, at each time step, it turns out that there is a region which is a white region. Okay? And do you remember what was the white region? The white region is the region of points from which you don't have a solution. These points are infeasible. If you start in here, you basically have too much inertia, momentum. You won't be able, there is no control input that is able to keep you within the blue box. Those are infeasible points. Okay? So we denoted the set of feasible initial state, the one which is this guy here. Okay? Calligraphic X0. Okay? Inside the red box, if you start in there, there is a solution to a finite time optimization problem. Okay? However, what can happen for the gray points, that if you start in here, you are feasible at time 0, but then you can go outside at the next time step, you can go outside the red box. So you start feasible, you become infeasible, even if there is no model mismatch. We had a nice discussion about this. Perfect model, just because you're short-sighted, you go out, and you start feasible, you become infeasible. So there was another set, which is the green set. Supposed to be green. Okay, and we call this set calligraphic, we call this set O infinity. Okay, it was the maximum invariant set. We'll discuss this set today a little bit more in details. The infinity in there stands for it's feasible at all time steps, so from 0 to infinity. Okay, that's why there is an infinity sign in there. So we said we want two, from a designer point of view, we want two properties. The first one, we want x0 to be equal to O infinity, right? So let's sort this out. We say we want one calligraphic x0. Or infinity. And why we want this? Because we want to know if we start feasible, we want always to be infeasible. Start feasible, we always want to be feasible. Okay? So if we are infeasible, we want to know when we start the system, not later at a later time. The second property is that we want x0 large. Right? Because 1 doesn't make much sense if it's true. Well, we have x0 equal to infinity, but x0 is very, very small. It means that our controller works only if, for instance, your airplane has a very low speed, your vehicles has a very low speed, and so on. We want to cover the largest set of initial conditions. Okay? So how do we get this? This was the last part of our lecture. We went, and we will start from there today. We said that there are two, so there's some summary here. We are going to change the optimization problem, the finite time optimization problem. We are going to add a terminal cost and a terminal constraints. And I'll show you how to add a terminal cost and a terminal constraint so that you have these two properties. Okay? There are two main approaches. The one is, at least we will cover in this class, two approaches. One is to say a very simple one, so to give you an idea of an idea of the technique, is to say that to set the terminal state equal to 0. So I have an horizon n. At the end of the horizon, I want to reach the origin. Remember, this is our simplest formulation in the MPC. We want to control the system to the origin. Okay, later in the second set of slides today, we will see more general formulation. For now, we just want to go to the origin while avoiding being infeasible. We want to stay within certain constraints. So just set it, go after n step to the origin, and this is going to work. So xf equal to 0. Okay. And so this xn equal to 0, which implies that we want the terminal set to be equal to 0. And by the way, if you are in 0, your cost at 0 is 0. So P of xn will be equal to 0. Okay? The proofs, so and then we'll discuss about, well, this works, but it's not really used, and I'll tell you why. And then we'll discuss about the approach number 2, which uses a more general terminal set and terminal cost. So there are two steps in the proofs. The proofs are dense, so try to follow me. There are 2 slides for each one, and the idea is that you have to capture the main idea. Okay, you will not. If you go in the book, you will see 2 pages of derivations. Just try to understand what is the main point of the proof. And there are 2 steps. The first one is, remember, this is about feasibility. You always want to be feasible. There is always a solution to keep you inside the blue, the calligraphic X. But you also don't want to wander around. You also want to converge to the origin. So the proof has 2 steps: feasibility and asymptotic stability. Let's start with the first proof: zero terminal state and first point. You are always feasible. Okay? As I mentioned last time, what is a common 10% of you will, you don't have oral exams, but 10% of my students at Berkeley say, oh, that's simple because I am at 0, I start a certain state, my horizon is n, and I force it to be equal to 0. Okay, so it's clearly as I move on, I will go to 0 because this is a constraint. It is not so simple because the constraint moves. This is a receding horizon. 0 to n, the constraint is at n. 1 to n plus 1, the constraint is n plus 1. 2 to n plus 2, the constraint is n plus 2. So you do have to prove that actually you end up in 0. Okay? So here is the feasibility. Here, the proof works as follows. Assume feasibility of x0. So at time 0, you are feasible. We want to prove that you will always be feasible. So if at time 0 you're feasible, then there is an input sequence, optimal, at time 0. U star 0, U star 1, U star n minus 1, okay? That will keep you inside the state constraints. So such that you generate an x0, x1, xn, which satisfy all your state constraints. If they satisfy all state constraints, remember the state constraints are, this has to be in x, this has to be in x, and this has to be equal to 0. This was your problem. You wrote your problem times 0 so that there is x, 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 and then the last step you have to be in 0. Okay? So there is no model mismatch. This is a proof without no model mismatch. So you apply, you start 0, because you started from here. Started from here. You apply, you start, this was your prediction, the blue line, okay? And you apply, you start 0, and you end up where you have predicted. There is no model mismatch, right? So the state at the next time step, x1, is actually equal to x1 that you have predicted at step 0. No model mismatch, and is ax0 plus bu0. Okay? Questions? The next time step. You start from x1, okay, which is now exactly equal to x1, and you don't know if there exists a feasible point or not. Okay, but here is 1. Okay, the control sequence, the shifted control sequence at the step 0, u1, u2, un minus 1 star, okay, augmented with 0 at the end is feasible. This is a conjecture, and it's very simple to prove. Everybody agrees? Why? Because if there was no model mismatch, you start in x1, and you apply the shifted sequence. After n minus 1 steps, you end up, so at this point here, you are in xn. Right? There is no model mismatch. After n minus 1 step, you are at origin. So you have to choose what is the last thing to do, the last step. Well, the last step you choose to apply 0, which implies that xn plus 1 will be 0, because this is a linear system. If you are in 0 and you apply 0, you will stay in 0. So 0 is an equilibrium point. And we obtained the main result, which is called recursive feasibility. Start feasible, you always be feasible. Did you get the main point? What is the tricky, or what is the thing you have to pay attention here is this. I'm not saying that at time 1, the optimizer will choose this sequence. This is not optimal. The star are just to make sure that you understand it is exactly this. Okay? But these are star at step 0. At step 1, the solver most highly likely will choose another sequence. Because this shifted sequence with 0 at origin is not optimal. I don't know what is the optimal step 1, but I know that there is one which is feasible. So in the worst case, the solver will pick this one. But if there is a better one that minimizes the cost, we'll choose that one. So the trick here is to say, in recursive feasibility, is to prove that there is a sequence, there exists a sequence, and then the solver will pick up a better one, but at this point you don't care. We are only interested in proving that if you start feasible, you will always be feasible. Questions? Very simple. Proof has always 2 parts, as I said before, feasibility and stability. So I've proven that if I start in this set, let's go back to this. We used red, I think, for calligraphic x0. So this guy here is calligraphic x0, which is also equal to O infinity. We just proven with x f equal to 0, we just proven this. You will start in there, you will always be in there. Okay? But I didn't prove that I will converge to the origin. So that's the second step of the proof. Okay, what is the main idea? The main idea is actually the one written in red here. We are going to prove that the value function, the optimal cost, is actually a Lyapunov function. You have studied Lyapunov theory in the lecture 1 and 2. We're going to use the results that we used in lecture 1 and 2 to show that the cost decreases along the closed loop trajectory. So if the cost decreases, you can, and this cost is quadratic, then you can claim that you have found a Lyapunov function, you found an energy function, and therefore you converge to the origin. So how do we start? Let's start with the cost, the optimal cost at time 0. J star 0 of x0 is Pxn plus the sum of stage costs, right? Pxn, I know that it's for any feasible solution, this will be 0. Because you can forget about the terminal cost, because in my problem, in xn, for every feasible solution, I'll be at 0. And so I'm left with the sum of stage costs, and I'm replacing at time 0 the u star 0, u star 1, u star n minus 1 to obtain the optimal cost. Okay? Then I try to derive j star x1 at the next time step. So what I want to prove is that from 0, the cost, which is a function of the state, j star, the optimal cost, from 0 to 1 decreases. Okay? And because j star is positive definite and is continuous, this will serve as a Lyapunov function. So here we have the same issue as before. I don't know what is the optimal input sequence at step 1. By the way, why do we focus only between 0 and 1? Because the system is time invariant. I could have the correct notation would have been xt given t and xt plus 1 given t plus 1. But remember, we have cleaned all the notation. We say 0, 1, very simple. The system is time invariant. Okay? It doesn't mean that the cost decreases only between 0 and 1. It will decrease between 0 and 1, 1 and 2, 2 and 3, and so on. So j star, I don't know what is the optimal cost when I start from x1. But I know a bound, and this is what's written. It's less or equal than the cost j0 tilde, which is the cost when I apply the shifted sequence. Okay? So what was the shifted sequence? Shifted sequence was u star 1, u star 2. Remember, I discard u star 0, u star 1, u star 2, u star n minus 1, and then 0 at the end. Right? So if you look at the cost, it looks like this. The sum goes from 1 to n, okay, of q xi u star I, which is the same as before. I'm using the same sequence as before, just shifted. 1, 2, 3, n minus 1, and then 0 at the end. So now I have to link this expression to the j star 0. So I want to understand if it's decreasing. Okay? So let's rewrite this expression as the sum from 0 to n minus 1 minus the cost at 0 plus the cost at n. Okay? Let's see, this is a very simple, let's go back. It's a very simple to derive this. Let's go to this slide here. Remember, the input sequence at time 0 is u star 0, u star 1, u star n minus 1. So the cost will have n elements, x0 transpose q x0 plus u0 transpose u0 and so on, right? So then you apply the shifted sequence, right? And I'm trying to understand what is the difference between these two. So what do you notice? First one, there is a u0 missing here, right? It's not here. Okay? Second one, at the end there is a 0, which is not here. Right? And this is what this third line is actually stating. The cost of the shifted sequence, okay, is the cost, the original cost, which is J star 0 at 0. You have to remove the first element and you have to add the 0. Remove the first element and add the last piece. Well, it turns out that this guy, by construction, we have added a 0 at the end to make it feasible. So it turns out that this is 0, okay? So really the optimal cost at step 1 is less or equal than this suboptimal cost, which we call J tilde, which is equal to the optimal cost at step 0 minus the stage cost at step 0. Okay? So, in summary, we have found that J star 0 of x1 minus J star 0 of x0, I'm bringing this term to this side, is less or equal than minus q x0 u star 0. The cost is less or equal, q, remember, was positive definite. The cost is less or equal than something which is negative definite. So the cost is decreasing in closed loop, the optimal cost. Okay? So q was positive. This is a negative number. Okay? From 0 to 1, J star is decreasing. It was positive definite. It was continuous. This is your Lyapunov function. We have proven asymptotic stability. That is your conclusion here. Questions? So in summary, what do you have to remember? For the lazy people, you have to remember the proof has only two parts. One is feasibility, the other one is stability. Okay? Feasibility means that you start feasible, you will always be feasible. And the way we have proven this is to construct a sequence that will keep you always feasible. But if you want to remember something more, the sequence is actually the shifted sequence. Very simple to remember. Okay? The second part of the proof is that not only I will always be inside my feasible set, I will actually converge to the origin. So asymptotic stability. And how we proved that? The proof was based on taking the optimal cost and proving that it decreases along the closed loop trajectories. It decreases once you apply MPC. And we have taken x0 and we have proven that J star at x0 we have taken x0, we applied MPC, we ended up in x1, and we have proven that regardless of the x0, see there is no assumption x0, so it can be any state, the optimal cost at the next time step will decrease. Okay? And so because it's positive definite, it's continuous, at origin, this is a Lyapunov function, and you will get asymptotic stability. The way we have done that, if you want to learn more, is actually to take the optimal cost at step 1, bound it by a suboptimal cost, which was the cost associated to the shifted sequence. Rewrite that as the cost at step 0 minus the first element plus the last element. And then because of the terminal constraint being equal to 0, this becomes this proves that decrease of J star. Okay? Good. So example of this approach, two-state systems, one input, two states. State has to be between minus 50, 50. The second state has to be between minus 10 and 10. The input has to be between plus 1 and minus 1. quadratic cost. This is my Q, and R is equal to 1. Okay? So what this example shows that how does it change the initial feasible set as a function of the horizon. Okay, so the designer here has used the project I just shown. Set up an MPC with xn equals 0. Okay? And you see the blue sets here are actually the calligraphic x0, which are equal to O infinity, okay, because of the proof that we have just given. There is, for xn equals 0, you always have persistent feasibility. So what do you notice? So this is where you want to get. You notice the drop, it's nice because we have the first property, right? You also notice that this is my big feasible set. We use the blue. Okay, red. So this was my calligraphic X. Okay. You notice that if the horizon is small, the set is small. So we don't have property number 2. Okay. So in order to have a larger set, I have to increase the horizon. As you increase the horizon, x0 will increase, and therefore O infinity will increase. Okay. Questions? So why do we need proof number 2? It's because trying to avoid this problem, because clearly you have an approach that guarantees persistent feasibility and stability, but to use it, you do need to have a long horizons. For this very simple example, n equal 20, it means 40 states, right? Because you have 2 states, you have 20 inputs. So you are going to have 40 plus 20, you're going to have 60 variables. You have upper bound and lower bound. For both states, you have 4 state constraints at each time step. So you're going to have 4 times 20. You're going to have 80 state constraints and 20 input constraints. You're going to have 100 constraints. You're going to have 80 variables. So this is going to be a problem which is difficult to solve in terms of milliseconds. Okay. So here is a second approach, a general terminal set. The idea behind it is that instead of using the origin as a terminal constraint, let's use this yellow set here. Okay, as xf. Okay, so what do we expect? If the terminal constraint is larger, the set of initial feasible states will be bigger, right? All the states that can, instead of steering I want to steer all the states with my limited input to the origin, I want to steer it to a bigger set. So what you see here is a little bit crowded. You will see that the feasible set for xn equals 0, let's use a red. Oh. Okay, this is this guy here. So this is x0 when you use the terminal constraint xn equals 0. Okay? And this is x0. When you use xf being the yellow one. Clearly, the x0 in yellow is bigger than the x0 in red. Okay? So idea is, let's get a larger set. And the proof that is coming next is to show how to choose this set and how to choose the terminal constraint into this set, the terminal cost into this set. Okay? So we have talked, we open a small parenthesis. We have talked about an invariant. This definition, this is this single slide that tells you a little bit more about invariants. Okay, and this thing that we have called O infinity. For people that want to learn more, there is in the book, there is a whole section on invariants. This course will not cover invariants. Okay, it's a more advanced topic. What you should remember is the main idea, and that there are tools in MATLAB in your MPT toolbox to compute this set. One line, you will give the system, you'll tell the constraints, and you'll compute the green set. Okay? So a positive invariant system positive invariant system is defined for a system without inputs. Okay? Could be an autonomous system or a system where you have already designed a control loop. So this is why CL stands for closed loop. Okay? You're given a system in closed loop where the control has been defined. Okay? And a positive invariant is a set such that if you start in there, you will be in there for all time instances. T n plus means t greater or equal than 0. Okay? So the very simple definition. I want a set for a system in free evolutions, okay, which can be a system without inputs or a system that had inputs and for which you have designed a controller, such that if you start in there, you will always be in there. Okay? And this nice picture shows, well, if your original set was where you want to keep your constraints, you want to keep your state into, okay, was the dashed one. Let's use blue. We have used blue for calligraphic X. Okay. What will happen is that this is where I want to keep my state in. Okay. What will happen is that some states will actually, if you start in there, will become infeasible. Okay. If you will exactly as the same arguments that we have done, that we have discussed before. If you start here, after one step, okay, you'll go out. Okay. So this is infeasible after one step. Then there is another smaller set, which is a set of states which will become infeasible after two steps. So you start here, then you are feasible, and then you become infeasible. Okay? So at the end, you basically want the green one. You want this invariant set. You want the set such that if you start in there, you will always be in there. Okay? And so you start green, and you will always be green. And this is the green one, is my O set. Okay? To be precise, O infinity. So what do you need to define an invariant set? Summary. So invariant sets are defined for systems without inputs. Okay? And you need to define the initial set calligraphic X. So I have a system, I have constraints. Tell me the set of states for which, if I start in there, I will always be in there. Okay? And this is MATLAB tools. There are MATLAB tools so that you give MATLAB tools that will accept a linear system, will accept a box, and will give you as output the green set. Okay? Let's close the parentheses and let's see what are let's go back to the MPC and our main focus, which is stability and feasibility. Here is the main result. Okay? There are three main assumptions. First one, very simple. We have already discussed this. Stage cost is positive definite, meaning strictly positive definite, and 0 at origin. X transpose QX, U plus U transpose RU satisfies that. Okay? I don't know if this works now. Second, just lost here. There's a little pin in front of the pen. Okay, yes. Okay, so first assumption, standard. Second assumption, yes, we can use a terminal set different from the origin, but has to be invariant. Okay? Has to be a set. If you land in there, there exists a controller V that keeps you in there. So you see, we had a linear system, and XF has to be invariant for the linear system when I use this controller V of X. Okay? So the set, I cannot choose any set. It's not going to work. I have to choose a set such that when I reach the set, there exists a controller that keeps me in the set for all time instance. So the controller is, that we have called it V. Okay? At this point, I don't need to know the form. I need to know that there exists one. Okay? Because remember, this is why we did the proof, the simpler proof first. The MPC doesn't need to know V. MPC will pick the optimal input. All what we need to know from a designer point of view, that there will always be a feasible choice. Okay? Third assumption, this was not present in the simple proof with XF equal to 0. Okay? That the terminal cost, so P, is a Lyapunov function in the terminal set. And the decrease is actually less than the stage cost when you apply this V. Okay? Let's take a few seconds to look at this and discuss them. Okay, let's discuss them comparing with the simple proof first, and let's remove all this writing. First assumption, standard. Everybody agrees? It was true also for xn equal to 0, just positive definite of the cost. Second assumption, was it true for the simple proof xn equals 0? Did we have that there or not? We did. 0 is an invariant. It's the smallest invariant possible. If you are in 0, there exists an input, which is 0, that keeps you in 0. Okay? And here I'm generalizing the concept. This is a set, such that if I am in this set, there exists an input. I have to call now, this input is more complicated. I have to call it V. Okay? It's actually a state feedback law. So that when you apply to the system, keeps you, if you start in XF, keeps you then in XF. So we had this property also before. We are replacing 0 with an invariant at the end. Third property, well, in 0, the terminal cost is 0. Okay, so there was no assumption on the terminal cost. Here, we are in XF. There is a terminal cost, and we need to make sure to design this terminal cost properly. Okay? The way we have to design it has to be a continuous function. Okay? And there has to be a Lyapunov function, meaning positive definite, continuous at origin, and it has to decrease along the closed loop trajectory. So it has to decrease from xk to xk plus 1, or from 0 to 1 for time invariant systems. Okay? And not only, this is not the only requirement. You see, there is an end. Okay? The decrease has to be smaller than the stage cost. Okay, it's an interesting property that you need to satisfy. If you design the MPC in this way, you will have persistent feasibility and asymptotic stability. Here is the theorem. The closed loop system under the MPC control law u star 0 of x is asymptotically stable. This is missing here. Okay? And the terminal set is positive invariant for the closed loop system. Okay? It means so probably need even to revise, you get a revised, there is even a stronger result than this, okay? The calligraphic x0, okay, which is the set where MPC is feasible at time 0, is actually the region of attraction. From all the states from calligraphic x0, you will go to 0, okay? Okay. Questions? So we have design MPC that provides feasibility and persistent feasibility. Persistent feasibility and asymptotic stability. Proof, same proof as before. I'll probably go quickly. How many steps the proof is going to have? 2. One is feasibility, the other one asymptotic stability. Okay? How is the feasibility proof going to work? Very simple. Start at step 0. Assume that you're feasible, so there is an input sequence u0, u1, un minus 1 that keeps you in the set, in the constraints. Remember now the constraints, right? They generate, this input sequence generates x1, x2, xn, and my constraint said this has to be in x, this has to be in x, and this has to be in xf. Okay? Step 1. Is MPC going to be feasible? Well, I don't know what MPC is going to choose as an optimal policy, as an optimal input, but I know that there exists one, because I can take the shifted sequence, u1, u2, un minus 1, okay? And at the end, instead of 0, remember 0 had the role of, if you are in 0, you apply 0 and you stay in 0. In the end, instead of 0, you apply this Vn, which by assumption you assume that exists. There exists a Vn that keeps you in XF. Okay? So if you do that, once you apply this input is feasible, not optimal, is feasible, you will generate an input sequence x1, from x1, x2, x3, x4, xn minus 1, and then at the end, xn will be in xf, which means that you can apply v of xn and be feasible. Okay? So the terminal constraint being an invariant guarantees persistent feasibility. Give me 1 minute to complete the proof, and then we'll summarize at the beginning of next hour. Stability. I'm not going to do the derivation. What is the idea? Optimal cost decreases along the closed loop trajectories. Okay? The optimal cost is, so you start from j star 0 next 0, and you see now why there are more lines, there is more form, because pxn is not 0. So there is more, pxn is different from 0, right? So you say, well, I would like to understand what is the optimal cost at step 1 for any generic x0. Well, you have to do the same derivation as before. I don't know what is the optimal input at 1. I use the shifted sequence, augmented with vxn. This is a suboptimal cost. Okay? You rewrite the suboptimal cost as the optimal one at step 0 minus the first step plus everything which is different at the last step. Okay? The same, trying to remember the same steps that we did for xn equal to 0. This will take us 10 minutes to do this derivation. It's not, you can do it easily at home. Okay? You just have to rewrite it as the cost of step 0 minus what was missing, which was the first step, because you have shifted now, plus the last step. Okay? And it turns out that this last step is exactly, will be, if you have the use assumption number 3, okay, this is p xn minus p at the next time step. Okay? And this is the stage cost at the next time step. You know that by assumption this is less than 0. This is why actually we need assumption 3. Without assumption 3, we cannot say anything about this term. So assumption 3 allows us to bound this term, and all what we get is, again, the stage costs, and we can claim that this decreases. Okay, let's take a break, and we'll start from here the next hour. It will be just a summary, so let's try to follow your slides if you can see the screen. Okay, summary. We said, beginning of this lecture, we said we have two issues. One is that we start feasible and we become infeasible. And the second issue was that even if we are always feasible, we might not converge to the origin. Okay? And we said, I'll give you two simple design approach so that you avoid this feasibility and stability issue. First one is it's simple. Your terminal set equal to 0. All what you have to do, there's nothing else that you have to do. You design your MPC, you set xn equal to 0. This is one of your additional constraints in YAML. I believe you're using YAML, right? You will use YAML. You just say xn equal to 0 and everything is going to work. Okay? The drawback, you know now that if you do that, what will happen is that will happen this here. Okay? That you will, highly likely you will get, unless you use long horizon, you will get a lot of infeasibility at the beginning. Okay? So then I gave you another approach, tell you instead of using 0, do two things. And this is the assumptions of your theorem. Okay? Use an invariant set. Okay, let's see if we can. So you have to do two steps. It's not as easy as setting xn equal to 0. One, compute an invariant set, a terminal invariant set. So you will need another piece of software that will give you this xf. Okay? And by the way, this xf is a function of your system, but also this terminal controller. Okay? Notice that once you have compute xf, your MPC design will just need to know xf, doesn't need to know v. Okay? The proof needs v. The MPC design just needs xf. Okay? This is again one of something which is hidden, but it's very important. You don't have to tell MPC there exists a v. Which v is it? Okay? You need to know that in xf there exists a v. MPC will find it for you because it looks among all possible feasible sequences and therefore all possible feedback laws, and you will find one that keeps you in there if there exists one. Okay? The second thing you have to do, you have to design this p, which is a Lyapunov function, and that's this decrease. So you have to do another piece of software that will give you this expression of p. Maybe you're looking for a quadratic function, so we'll give you the p matrix. And you have to use the p matrix as a terminal cost and xf as a terminal constraint. And you will get, if you satisfy 1, 2, and 3, you will have persistent feasibility and asymptotic stability. Okay? So the proof is identical. You have to remember this proof. And by the way, this will be subject of exams. It's very similar to the xn equal to 0. It's the same steps. The two main steps are first, persistent feasibility, second one stability. Persistent feasibility is shifted sequence, and at the end, what keeps you in the terminal set, and we called it V. Okay? That's all. And you know that MPC will not pick at the next time step this one. Highly likely will not pick. It might pick, but in general looks for a better policy. All what you need to know is that there exists a feasible one. The second step is again the same idea of using the cost to the optimal cost, J star T of xt, that because our system is time invariant, we call it J star 0 of x0, and show that it decreases along the closed loop trajectories. So the way that it decreases, you have to start from any x0, which could be any xt, and show that xt plus 1, J star optimal, so J optimal, so J star decreases. Okay? And so the way you show this is that I don't know what is the optimal input at the next time step, but I know a suboptimal one, which is the shifted sequence, U1, U2, because this now starts from 1, and the augmented one at the end with V. Okay? And now you have to link this suboptimal one to the optimal one at the previous step. And remember, because we shifted, there are two main differences. One at the beginning at 0, the other one at the end. This is the difference with the 0, and this is the difference with the end. And actually now you understand why assumption 3, because assumption 3 just says that P at the next time step minus P at step n is less or equal than this quantity. And therefore, you can make all this quantity negative. Right? So this is your main assumption 3. And therefore, this is your result. These terms, you can forget about this term and say that J star from one step to another one decreases and decrease of the stage cost. Okay? All these assumptions are sufficient conditions. Okay? Could you do better? Could you have a less strict? Ja?
Om 11 uur komen we voorbij. Is goed? Dit gaat op 10 minuten. De bal gaat bevoren. Oké, goed. Om 11. Oké.
Welcome.
That should not be part of your review of the lecture. Not our fault.
Okay, let's move forward. What I was discussing this term here, okay? By assumption 3, this term here is less or equal than 0, okay? So it's negative. Could it be a little bit positive? Yes or no? What is this is, you have to compare this with this, right? All what you want that this term is less or equal than 0, right? So yes, it could be a little bit positive as long as it's bigger than, as long as it's smaller than this quantity here in absolute value, right? So again, this is to show you all what you want that it decreases, okay? A sufficient assumption is this one here. You can make the theorem more complicated to have a less stringent condition and have a different type of condition, okay? But this is more subject advanced topic. Let's go summary. Let's do an example. Let's take, so far we had linear system and any cost. We called it P and Q. To be precise, this is, all this proof has nothing to do with linear system. You can put, there is a slide at the end. Did we use linearity at all here? No. Okay, this holds for any nonlinear system, any cost, as long as you satisfy the 3 assumptions, okay? For linear system and quadratic cost, it's just easier to compute this, the terminal set and the terminal cost that satisfy assumption 2 and 3, okay? So I have a linear system now, and I have a quadratic stage cost and a quadratic terminal cost. So I want to, I have polytopes, so x and u are polytopes. And now we are in the setting where we can compute stuff. MPT toolbox works for this. Linear system, linear inequality constraints, quadratic cost is simple to design a MPC which is persistently feasible and stable. Okay, here is the steps. Here is how I suggest to design to satisfy the three assumptions. First of all, you design an unconstrained linear quadratic regulator. Take this linear system, forget about constraints, design an LQR. MATLAB command DLQR, right? Discrete LQR, and it will give you F infinity. Okay, once you have chosen your Q, R, A, and B. Okay, it also gives you as an output the optimal cost, P infinity, right? So LQR command will give you, in MATLAB, will give you F infinity and P infinity. Step number 2, choose the terminal weight exactly as P infinity. The P, which is the terminal weight of your MPC, okay? I'm saying choose it being equal to the infinite time cost of the LQR. Okay? What are you left to design? So I've chosen the terminal cost. I have to design the terminal set. Okay? Terminal set, I'm suggesting do the following. Compute the maximum invariant set, so it's the largest invariant set, for the linear system once you apply the unconstrained LQR. This is this guy here. Okay, this is the linear systems. When you apply the unconstrained LQR, linear, it was AX plus BU. U is F infinity XK. So this becomes now an autonomous system, a system without inputs. This is the closed loop system. And I'm asking, I will ask the software, compute the set X, the largest set XF, such that when I start in there, I will be in there at all time instance. There is a typo here. This is F sub infinity time xk, right? Okay. And to the software, you also need to tell which console. I remember the invariant set was defined for a system with constraints. Software, you have to give the dynamic matrices of the system. So you will tell A plus B F infinity. That's my dynamic matrix. Okay. A plus B F infinity is my A closed loop. You also have to tell which constraints you want to satisfy. Well, you want to be satisfy the state constraints, so you want to be always in X, okay? And you always want to satisfy the input constraints of the LQR. The LQR has to satisfy input constraints. But the LQR is F infinity times XK, right? So this becomes a state constraint as well. F infinity XK has to be in the polytop U, and xk has to be in X. Okay? Questions? So the next slide should be, well, if you follow step 1, step 2, and step 3, all the 3 assumptions of the theorem are satisfied. Okay? Stage cost is positive definite. By construction, the set is invariant under the local controller. Now the V, it's the LQR, okay? And if you do the math, this P infinity in the terminal set decreases and decreases more than the stage cost, okay? Which is X transpose Q X. We're not gonna do the math, but it turns out that once you do, this is P at XK plus 1, minus P of xk. You write down the expression of, xk plus 1 is equal axk plus buk. And once you write down everything, it turns out that this is nothing but the algebraic Riccati equation. So it turns out that this is you can use the expression before in the previous slides, okay, to bound this term, and the bound is exactly minus x transpose qx. So this satisfies assumption 3 satisfied, okay? Questions? So again, the three, what you have to remember is that the three assumptions, assumption 1, 2, and 3, have always to be satisfied. And the theorem is very general. It works for nonlinear systems, any cost. I've told you in this slide 643 tells you a design procedure, a detailed design procedure for satisfying the three assumptions. Okay? It says for linear systems and quadratic cost, do LQR, choose the terminal cost being the infinite cost unconstrained of the LQR, design the maximum positive invariant set once the closed loop system is the LQR, and you're done. Okay? So going back to let's do an example. Here is a two-state system. I believe it's always the same, between minus 50 and 50, minus 10 and 10, one input, upper bound and lower bound on, you have input constraints, Q is equal to identity, R is equal to 1, okay? And you are asked in your exam to design a stable, asymptotically stable and a persistently feasible MPC, okay? The first approach is just use xn equal to 0. That's one approach. Let's use the more complicated one, the less conservative one, using a larger set as a terminal set. And so, first of all, you compute the LQR, and LQR as an output will give you the gain and infinite cost. Okay, this is in MATLAB, I believe, if it's still the same, it should be DLQR. Remember, DLQR as inputs the system matrix A, B, Q, and the cost, right? Q and R. This is A, this is your Q, this is your R, this is your A, and this is your B. Okay? You do that. Once you do that, you compute P, you set P infinity is a matrix, will be a 2 by 2 matrix. Your terminal cost has to be exactly to this matrix. So you have one variable, one of the two knobs, the terminal cost and terminal constraint now is set. You have to compute the terminal constraint. Well, compute the maximum invariant set. There is an MPT command for that, which I forgot now, MP 3.0 what it is. You will learn it today, where you have to give the closed loop system. You have to give a closed loop. ACL, and in this case you will use A plus B times the closed loop LQR. This is going to be your A closed loop, okay? And you also have to give, so this is the system dynamics, you have to give the state constraints you want to be in, okay? The state constraints are the original state constraints, AX less or equal than BX. This AX and BX will be nothing but minus 50, 50, and minus 10, 10 for the second component. Okay, this is EX and BF. The second, don't forget that this will be the state constraints, but you also want the LQR to satisfy the input constraints, right? And that's why this second set of constraints, these are input constraints for LQR. Okay, AU times U less or equal than BU. So you want between minus 1 and 1. But the U that you're going to apply in XF is the LQR, which is F infinity X, and that's why it becomes a state constraints. Okay? The MPT toolbox, once you give AX, once you give once you give the closed loop system, once you give the set of states that you want to compute, so this is 1, this is 2, it will give you as output, this is the invariant. Okay, will give us output a small set. It looks very small, yes, but this is an invariant, and this is better than 0. Okay? Questions? What is coming next is just a simulation of this design. You will see, I believe you used horizon 10. Okay? So you start from this set, you start from this point. You are feasible at time 0. You see that there is an input sequence that brings you in the terminal set, in the invariant set in 10 steps. Okay? You basically are done. For this, for all the set of initial points that are feasible at step 0, you know that you will always be feasible and you converge to the origin. This was our proof before. Okay? What is interesting about this? That there is no model mismatch. You apply U1. Where are you going to be at the next time step? You're going to be here, right? As you have predicted, because there is no model mismatch. Okay? From here, you run MPC. And what is the optimal input sequence? Well, this is the optimal input sequence. I'm going to flip between the two. Sorry. Should flip between the first and the second one. First and second one. So you see that we are not using RQR because we are not. The theorem uses as a shifted sequence when you are in 1. Okay? Once you end up in 1, you would have used the one before and then in XF the RQR. That's not what MPC does, because that's not optimal. That was suboptimal. The MPC will change slightly. See, we'll go in XF only at the end. Okay? Can you notice this? Look at this part here that moves and becomes here. It goes here. Okay? And so on. So you go next, you keep, your open loop prediction are always different than the closed loop prediction, but you end up, because we have proven that, you end up in closed loop, which is dark, you end up in the set. And this is the optimal cost as a function of time. This is J star of 0 as a function of x of k. Okay? You see that it decreases, so it's a Lyapunov function as we have planned. Okay, I think we are done with this lecture, part of the lecture. Summary. Okay. What do you have? Takeaway point, terminal set, terminal costs in order to ensure feasibility and stability. Okay, that's this tuning knob that you have, and I gave you 2 approaches to design this set and this cost. What is interesting is that are they really used in practice? You will hear it tomorrow. Okay. At this point, generally not. Okay. The first reason because this is not well understood. Okay. And the second reason is that it does require advanced tools, and some of these tools have been developed here only in the past few years. Okay. So I would say they're starting to use it in practice, but at this point, in practice, it's just you will have a point here. What you do in practice, you do lots of simulations, and you basically see that there's an invariant by simulation. You will see for which initial condition the system converges. Okay, just lots of simulations. In general, if you have a terminal set, reduces the region of attraction. Okay. And so what does it mean? It means that if you are infeasible, you need a strategy to recover from infeasibility. Okay, and this is part of a controlled partitioner design. Okay, and this. And if you have a stable system with a long horizon, it depends on the system. Do you really need it or not? Sometimes you don't need it. Okay, it's for stable system and long horizons. Unstable system and short horizon, you do need it. Okay. Again, another summary. These are all sufficient conditions. The regional attraction without terminal constraint may be larger than MPC with terminal constraint. Let's focus a little bit about this point. Okay. So we have designed this theorem so that x0 is O infinity. Okay. But if you go back to the previous slides, I could actually forget about the terminal state, not use it, and I might have a larger regional attraction. I might have a larger O infinity. Just x0 will be different from O infinity, right? So remember, we wanted this guy, okay? And our design is so that x0 is O infinity. What if I don't forget about this theorem, okay? Or if I don't have x0 is different from O infinity. Well, if I can compute O infinity, it's not a problem. I will use O infinity as my design specification. The system works in O infinity with MPC. Well, the problem is that it's difficult to compute O infinity for the closed loop system, because MPC is a complicated control that comes out of an optimization schema, okay? And so it's not as simple as computing O infinity for the LQR, okay? So this is what this point here is telling you. If you avoid the terminal set, the region of attraction without, so O infinity without terminal constraint might be larger with the one with terminal constraint. But you don't know what is O infinity, okay? O infinity is difficult, extremely difficult to compute, okay? X0 is the simplest choice, but then you need large N. I showed you an approach for linear system with quadratic cost. What is all the world basically is using is long horizon and just do a lot of simulations. Sample from this condition, and so on. And clearly, if you have a horizon long enough, instead you are not short-sighted anymore, and then you have the best that you can do, okay? This example, you have to go back to your, do you remember the Cessna example? Okay, the way we started this set of slides was, okay, the Cessna was a cool example with n equal 10. It could satisfy input constraints, rate constraint, and state constraint, but suddenly if you had n equal 4, it was unstable, okay? This goes back to the Cessna example and said, yes, n equal 4 was unstable, but if you do the approach that I showed you, with terminal costs, terminal constraints, you are stable and feasible, okay? Summary, this slide just keeps repeating what I already said. One last slide. I already mentioned this during my explanation. The assumptions on the terminal set did not rely on linearity. We did use time invariance. A colleague of yours had a question about time varying system. That's an interesting topic, but not covered in this class. As long as it's time invariant, you have seen that I've never used linearity. I never used that the cost was quadratic. It could be piecewise linear, okay? So all the theorem, okay, is valid for as long as the cost is positive definite, as long as you satisfy the three assumptions, it's valid. What is the problem is that, of course, XF and P, so the terminal cost and the terminal constraints, are difficult to compute for nonlinear systems. There is, at this point, I would say there exists no tool that like the MPT toolbox, that you can provide a nonlinear system, a set of nonlinear equation, a nonlinear set of constraints that will give you XF, okay? And this completes this lecture. Professor Morari will then start from, as a reminder, first of all, questions. No questions? You don't want to know what the questions you'll be asked in the exam? This is usually the one I get at Berkeley. What is the exam going to look like? We are going to go to the slides, practical. Then tomorrow morning, Friday morning, you receive an email. Friday morning, 8:15, we'll go to hybrid. And then we'll do explicit, and the class will be over. Okay?
Okay. We'll shift gears now. In the following sense, Professor Borelli gave you an outline of the work that was done over the last couple of decades, I would say, on stability, feasibility, and how to guarantee those properties by design. And as he mentioned, those are important theoretical concepts. They give you some insight into regions of stability, how they changes with tuning parameters, etc. But as he mentioned at the end, they are not concepts that are very often used for practical design, okay, because they are complicated to calculate. Okay, and what he mentioned at the end, there's no tool really to do that for nonlinear systems. There's no practical tool now, I would say, unless you are in 2 dimensions. And I would dare saying that there will not be a practical tool to compute this for nonlinear systems except in two or three dimensions anytime soon. So those are things that are good to frame your thinking about the technology, but it's not what you're going to use when you do applications. Okay. Contrary to this, the aspects that I'm going to discuss now, they are extremely important for applications, and they're all used all the time in applications, okay? Because they help you in the performance of the controller. They're essential, like tracking. So it's like talking about integral control. In a sense, it is talking about integral control in classical control theory. All we have discussed now, when you talk about stability, feasibility, etc., that Professor Borelli mentioned, that assumes perfect model. Okay, I know everything about the system, I have a perfect model, and then this will track, this will converge, will go to zero, and all that. But even if you have a slight error, all those controllers will have offset. Okay, so it's like a proportional controller. It has no integral action in there. And so the first thing we're going to look at is how to fix that. You know, how to augment this controller, the framework that you've heard about, and get you no offset properties. The second is soft constraints. Now, what is that? We talked a lot about regions, computing regions, invariant sets, etc. Actually, if the system is open loop stable, and most systems, fortunately, are that you work with, open loop stable, and the second thing, if there are no state or output constraints, hard state or output constraints, that means strict bounds, most of those regions don't exist. It's all infinite. Okay, so you greatly simplify the problem if you don't have those hard constraints. But you still want to have constraints on your states and outputs. But you can do soft constraints, and that preserves the simplicity, but gives you some bounding of the control action. So that's something that's used, very common, has been used for lots of years. And there's a way of doing it well and a way of doing it not so well, and that we'll discuss. And the final couple slides are going to be just to simplify the optimization problem that you have to solve online. Okay, so those are the things I want to discuss now. And obviously at 11 we'll have to stop for some time for them to fix the lights. But we'll move on to the tracking problem. Okay, what's the problem we take? We have this linear model that you have seen lots of times. What does tracking mean? Tracking in our context means we want yk, the output, to go to some reference r as k goes to infinity. And so you remember your objective function in the MPC controller. You have some terminal weight on x, and you have some weight on x over time u. The first thing you need to do is this formulation that we learned about assumes that the desired state is 0. X goes to 0, u goes to 0, etc. Now, if you track, x does not go to 0, y does not go to 0, and u does not go to 0. So the first thing you need to do is, when you have given some reference that you want to follow, and the output yk should follow this reference, ck is equal to r. If that's the requirement, then you want to calculate the appropriate targets that allow you to reach that. So what you do is you set this top equation, you put it to steady state. So what does steady state mean? Steady state means, oops. A steady state means that, means xk plus 1 is equal to xk is equal to, what's it doing here? Is equal to x as steady state. Okay, that's the assumption. So you substitute this in this first equation, and you get the equation down here. XS is equal to AX plus BUS, and then obviously the output Y, okay, is equal to CXK. That becomes here CXS is equal to R. So you have this system of linear equations. You have given R. Okay, R is obviously given. That's your, those are your set points. And so this system of equations, assuming it has the right dimension, meaning you have at least as many u's as there are, at least as many degrees of freedom, u, as you have requirements, r, steady state points. Otherwise, you cannot solve the system of equation. But if you have the dimensions, you can write this system here in this linear equation form with this matrix I minus A minus B CU. You can rewrite that is equal to R. And if this matrix I minus A minus B C0, if this matrix here is non-singular, okay, you can calculate what is X, S, and US given some reference R. So given some set point R, you can calculate at this, ideally, if you know the model, given some set point R, you can calculate what are the states and what are the inputs that give you those set points. That's what we are doing here. So it's a very simple linear calculations, given the set points, what is X and U to give you those set points. And those are in some way our targets, okay? And that's what goes on in the next slide, then the steady state problem. So we have here repeated exactly the system of equations that I gave you on the last slide I showed. And we say now, okay, what if the system has not one solution, but if it actually has many solutions? So this would be, for example, the case when dimension of u was m, and dimension of y was p. So if m is greater than p, so this is the dimension of u is equal to m is greater than dimension of is greater than p, which is the dimension of y. Okay, so meaning if you have more degrees of freedom, more inputs u, then you have requirements, set points r. Okay, if that is true, then there are many u's that do the job, and then you can set yourself an objective as indicated here. An objective that I want to just the smallest u's, okay, in this sense, in the sum of squares sense, that satisfy that system of equations. Okay, you can also put some other objective, but you want to have a unique u as a target, and all u's that you get here satisfy, and you pick here the smallest one that does the job. You can have the other extreme, actually, that there is no u that does the job. So that would be in the case that actually this inequality here goes the other way, would be one reason, or in whatever way that this this matrix here happens to be singular or not a full rank, so then there exists no u that does the job. Then you can say, okay, what I would like to do is just, this is the error, this is Cx, which is the output minus the reference, so this is the error here. This here is the error. Okay, if this, you want to make this error as small as possible, so this problem down here minimizes the sum of squares of error, so you're trying to find the u, which will not do the perfect job, but it will get you as close as it can, given the system, to the set point. And you will calculate this x and this u that does that job. Okay, so that's the details of the target computation. At last slide I said you compute the unique target, that's fine. More general is that you have many ways to reach the targets or no way to reach the target, and so then you solve for the target this other modified optimization problem. Somebody here? We'll get the guy. Not yet, so we can continue because we'll have to take a 10-minute break for them to put pull the plug and reboot. This is the MPC problem we'll then solve after we determine the targets. And so you see the changes from before. What are the changes? They're just, we didn't have a CXS here, we didn't have a CXS here, and we didn't have a US here. So those are now, we don't penalize the U's, but we penalize the deviations of U from the target, the deviation of Y from the target here and here. And obviously we have the same problem, same model, same constraints, same initial condition, etc. However, the issue is that this controller here will still, it's better obviously than before, but this controller has still no provision to reduce offset. Okay, we'll have yet now the better target, but it's all still dependent on the model, and it will show offset if you have some model error, disturbances, and so on. So that's the first step toward coming up with a controller that gives you no offset, because you have these targets, the non-zero targets. But now we'll still fix the issue with the integrator, and we'll do that after the break, after we reboot the system. Thanks. Okay, we'll continue. As said, there's no microphone. There's some recording here. We'll try to patch it up with the slides that I will be presenting and discussing. So we'll have some maybe lower quality recording. Going back to this problem, I outlined you the problem. So now we'll look at the issue that we want to do reference tracking, but we want to do reference tracking at least asymptotically without error. So we want to get the same type of performance that you get when you have integral action. Integral action gives you, as you know, no offset for constant set points. Okay, if you have integral action and you have a step change in the set point, then eventually, asymptotically, because of the integral action, you will reach the set point without error, and it doesn't depend on your model accuracy that you have or anything. It just depends on the integral action, and the integral action will give you this behavior. And so we want to achieve the same behavior here within the MPC context, with the modeling, with the prediction, etc., but with an additional feature that it does asymptotic, error-free tracking for asymptotically constant set points or references are. And so in this case, it is not really necessary that we assume the model to be linear. Okay, the model is the real system we don't know. Okay, just like with integral action, you don't know what the real system is. Maybe nonlinear. It is actually nonlinear, and that's what indicated by this description here. And we don't know that, okay? So that's the real system. We don't have, I just write it in this general form. And so the goal is to design a receding horizon controller in order to make the output Y track the reference signal such that eventually Y goes to R for t is equal to infinity. And so we assume now that the set point is constant, as I mentioned. And so the first thing we do toward achieving this is we choose a linear model, and the linear model is the same linear model that I have here. So we have xt is equal to ax plus bu. So, okay, that's our linear model. But now we add something to that model. We add a disturbance, okay? And that disturbance is this disturbance d here. And what we also added down here. And we assume that this disturbance is constant. So what's the model, the dynamic model of a constant disturbance? That is here. dt plus 1 is equal to dt. So it doesn't change, it's the same. So that's that's just a model for a constant input. And we will not know this constant input. Okay, that's some disturbance that happens to affect the problem, but we don't know it. And so what we want to make sure is that we can get a correct tracking of this y
even when we don't know the disturbance. So this is now what I wrote down here at the bottom here is our model that we will use for controller design and also for observer or estimator design. This is the model that we will use, and the major new feature or characteristic of that model is that now we'll have some additive, we assume that we have some additive constant disturbance D that is added to the output and added to the input. And you will see later, kind of get a sense what this additional disturbance does. Okay, next step, which we have not done before, but which we do now, new, but I mentioned it, and we discussed it on day 2 of the lecture last week, is that we will build an observer, an estimator, for this system that I showed you on the last slide. For this system at the bottom, okay, and this is now a new special type of system, and actually, if you look at it, this is now my system equations, okay, and one part of the state of my new system is X, and the other part of the state of my new system is D. So this here, X and D, is my new state of the system. Okay, so this augmented disturbance is an additional state that I will estimate through my observer. And this is very common. You do that. That's in the lecture that I skipped on day 2. Okay, that says modeling uncertainty. Okay, in this lecture, you have a little bit more detail on this material, namely that you augment the system state with a disturbance state, and this is now what I will estimate using my estimator that I showed you already at the next slide. So what you see what the estimator does, and it's the same principle, estimation principle that we introduced. I have, if you look at it, I have here on the top exactly my model from the last slide. Okay, that's exactly, except that now I have an X head and a D head, which means my estimated state and disturbance. Plus, remember, in order to have good properties of my estimator, I cannot just use the model, but I also use a correction term, and I correct my estimate based on the difference between my measurement and the estimate of the measurement. Okay, so I have now a correction term. So this whole thing is a correction term. Okay, and this here is my estimation error. Why? Because the first term there is ym, that's my measurement, and the second term cx plus cdd is exactly what on the last slide I wrote down is my output. Okay, I don't want a page because then I lose my drawings. Okay, so on the last slide you had y is equal to cx plus cdd, and that's exactly here the difference between my true measurement and my estimate of the measurement according to the model I assumed on the last slide. So this here, what I wrote here on top, is a standard observer or filter for the augmented system I defined on the last slide. What I don't know at this point, I have an LXLD, and remember that was our observer gain or filter gain. And we discussed on how to calculate that. You discussed it such that the observer is stable, and we discussed how to do it optimally by solving this Riccati equation for the Kalman filter. Okay, so there are procedures on how to calculate that LXLD, which is just written here in 2 portions, but it's just one observer gain that you can calculate from the Riccati equations. And this is now separate before we start with any MPC. This is just state estimation. So we estimate the states of our model, and we estimate an additional state, which is this disturbance D. And that's the critical component. Because we have written it in this way, we have the following lemma down here, which kind of defines what this observer does and what we want it to do. And the lemma says the following. It says that suppose the observer is stable. So that we can easily do when we have conditions satisfied, Riccati equation, Kalman filter, we can make it stable. Okay. And then here it says the number of output equals the dimension of the constant disturbance. So what does this mean? That means we have those D's, okay, that we add, and we add as many D's as outputs we want to control. That's all. Okay, so for each output Y, we add a D. Okay, so that's the same dimension. If this is the case, then the observer steady state. So that means this observer here, okay, it's going to, with constant input, obviously, it's going to converge to some steady state. So this observer steady state obviously is the X steady state and D steady state. So X infinity, I call it here, and X infinity and D infinity. Okay, that's what this is converging to. Okay. And obviously I have some U, which is constant, which is this U infinity here. So this observer steady state, so this, if everything is constant, it will converge and will converge to this, to a steady state defined by this linear equation here. Where Ym infinity, that's my measurement, my true measurement, not model, that's my true system measurement, and U infinity is my true input that I send to the system U infinity. Now, what does this complicated expression mean? It means, in particular, the second equation. So if you look at it, the second equation here, what does the second equation tell you down here? It says Ym infinity, and putting this term on the other side, Ym infinity is equal to Cx infinity. Okay, let's write this here. Ym infinity here is equal to Ym infinity is equal to Cx head infinity plus Cd d head infinity. Okay. Now what I wrote down here at the bottom, that is the equation for my measurement. That is the estimate. Cx infinity plus Cd infinity is my estimate of my measurement. And it says that this is equal to my measurement. Okay? So this observer has the nice property that it will drive my estimation error to 0. Okay? So this will give me no offset in estimating my measured output. So basically, this observer will make this estimation error up here equal to 0. Now, can we understand why this is the case? Yes, it's not difficult. Okay, what we have to do, and now I'm erasing this to be able to write some more. So this is the error. Okay, now why does this observer drive the error to 0? Because if you look at the second line here, it says dt plus 1 is equal to dt plus LD, so I'm looking at those terms, dt plus LD times this expression here. That's the second line. So it says disturbances time t plus 1 is equal to disturbances d plus this term. Now, if this term, this error term, okay, if this term doesn't go to 0, the disturbance grows. dt plus 1 is equal to dt plus the error term, it will continue growing until what? Until this error term is equal to 0, assuming that this matrix LD here is a full rank. Okay, because otherwise there may be some 0 direction where I don't see that error. Okay. But that's just an kind of a plausibility consideration, but the property of this observer, and that's very important, I have designed an observer that will give me no offset in my estimate of my output, which I compare to the measured output. And it doesn't matter if my model that I have here, A, B, C, D, is wrong. As long as the observer converges, it will converge to the correct output. Just like what an integral controller does. I have no error, even if I have no model, as long as it converges, as long as it's stable. That's the property of this observer. Okay, so I have a special observer that gives me zero tracking on my measured output. Okay, any questions on this? If not, we'll continue. So this here at the bottom is exactly, at the top is exactly the bottom equation I had on the previous slide, which is the condition here. And so we derive from this the insight. So I have an expression of what steady state x's and u's I need, okay, to get this output be tracked perfectly. And I will take those steady states and I use them as targets now, just like I did before for my MPC controller. And so there's a slight correction here. I saw it just before, so here there should be also written target, comma, infinity. So I will use exactly this expression, which I know is the steady state condition satisfied by my observer. I know that. This is what this observer will converge to. I will use this to define my targets for my controller. And what will happen, and what else I changed, obviously, I changed the measured to my desired reference. So that gives me the target. I want eventually my measured to be my desired reference. And so this is now the system of equations I will add to my MPC equations, okay, in order to define, just like before, my X target and U target, which will then appear in the objective. And let's see that in the next slide. So I have now here my X target, and my U target, which are the X and U targets from the previous slide, which is the system of equation that I repeated down here. So how do I get no offset? What to do? First of all, I use this special observer. I have to use this special observer that I showed you with the augmented state where I estimate the disturbance of the state. That gives me an X head and it gives me a D head. Okay, that's my estimate. And then I can use this D head here. Okay. I can use it to define in this lower equation my targets for the MPC controller, and this XT and the UT goes in here, and otherwise here I have exactly basically the same equations I had before: my system model, my constraints, my disturbance equation, my initial initial condition for the prediction here starts with the estimated state. The initial condition for disturbance, this starts with the estimated disturbance, etc. So I have now one more equation. This was the standard equation. This is my augmented equation. Remember, this is what I added to the system of equations. So I have this equation here, system equation plus this, and accordingly this initial state for X and D. Otherwise it's the same MPC, but in addition I have this equation that I need to solve when I have this, let's say, quadratic program. I solve the quadratic program subject to those equality constraints, subject to those equality constraints, etc. But it's basically again a quadratic program. And the nice thing, this fix with this observer to estimate my constant disturbance, that was the trick, my estimate constant disturbance, gives me now a formulation here that gives me where I can prove that there's no offset in between my references and my measured outputs y. And this is summarized in this theorem, but the theorem doesn't say much more than what I said here. So it says basically, I'm not even going to go into the details, it basically says the setup that we generated, that I wrote, that I defined for you, gives you no offset in your control. And because in industry, clearly, or for many practical applications, it's very important to have no tracking error, even if your model may be changing, may be inaccurate. This is a very important feature of most MPC controllers that you would implement. And actually for this here, you can also show that with some minor assumption, all those stability considerations, etc., the invariant sets, target regions, etc., carry over to this MPC controller and this general formulation. Okay, one minor final comment on this whole methodology. We skipped the question, I omitted this, is what is BD and CD, okay? Because if we look back now at the slide where we introduced this, okay, we said here we have a disturbance, a model with a disturbance. This was our new system model that we're using. We have introduced this disturbance, this additive disturbance, but we never talked about what this B and C should be. In principle, it could be anything. But can it be anything? What are the restrictions on the choice of that B and D? How that disturbance affects the states through the matrix BD, and how that disturbance affects the outputs through the matrix CD. Okay. How do we have to choose those? And the first simple thing you say is, okay, forget about this. I choose B0, okay? And this CD, I just choose identity, because I need the same number of disturbances as outputs, so I may as well choose just identity. Okay, so that's one idea. And we'll look now back to the slide 6. Okay, it says the following. Choose CD is equal to identity. Okay. What do you need for observer design? For observer design, as I mentioned to you, for the Riccati equation to converge, you need this system here. Okay, so this system here. This system must be observable. Why? Because we showed before, for observer design, you need at least detectability. Here it turns out, because of the special structure, you actually need observability. Okay, I can explain this separately. We need observability to solve the Riccati equation. In order to design observer gain, we need observability. Now, what's the observability of the system? You now have a special system. The observability has nothing to do with you, okay? Inputs has nothing to do. But what do we need to look for observability? We have a system matrix that looks like A, B, D, and the other thing is C. Sorry. A, B, D. Okay, then here is 0, and here is I. This is the second equation, so this is one matrix, this is the matrix. And then we have the C matrix, and the C matrix is C, and we have, in principle, CD. Okay, in our case, so this is the pair, the new, if you want, this is some C prime matrix, and this is some A prime matrix, okay? So we need this pair of AC, we need this pair of system matrices, A and C prime, we need those to be observable. So what are the conditions that A, this first A prime and C prime together, what are the conditions that is observable? Okay. And this is what's written at the end here with the assumption that CD is equal to I, then this matrix that I looked at, this observability condition, you can show that is observable if and only if two conditions are satisfied. First of all, the original system, CA, is observable. Not my C prime A prime, but my original system CA has to be observable, plus a second condition, namely that the determinant here has to be not equal to 0. And this determinant has in here, now we'll just hope that it doesn't turn off the light before we are done. So this CD is equal to I, so it has this BD in there, and so that means this condition tells me how I can choose BD. I can only choose a BD such that this matrix here has determinant not equal to 0. That's my restriction. Once I select CD is equal to I, okay, a simple disturbance at the bottom, I have to select BD such that this determinant condition is satisfied. That is a restriction on my disturbance model, how I can choose the disturbance to affect the states. I can say, okay, what's a simple thing? Simple thing is I select BD is equal to 0. How about that? I can do it if the determinant of A minus I is not equal to 0. That's the conclusion now. So tell me, what does it mean in terms of the eigenvalues of the matrix A, restriction that the determinant of A minus I is not equal to 0. So this, I want to look at this condition. I want to hear from you some statement on the eigenvalues of the matrix A that would make this determinant not equal to 0. So what's the condition of the eigenvalues of the matrix A? Exactly, okay? Because how do I find the eigenvalues? I find the eigenvalues that the eigenvalues would be determinant A minus lambda I is equal to 0, okay? Where lambda is an eigenvalue. Now we have a special case that actually lambda is equal to 1, okay? So if this is the case, the determinant is equal to 0, then there is an eigenvalue 1. And so as your colleague said, what this means that none of the eigenvalues of A are allowed to be equal to 1. What does this mean in terms of the practical system? I is an integrator in discrete time. So that means A, the system, must not contain any integrators. So if the system doesn't, and this is what's the remark here, if the system has no integrators, then we can choose a very simple disturbance model, namely BD is equal to 0, CD is equal, BD is equal to 0, CD is equal to I, and we can design our observer and get this no offset property. If we have integrators, we cannot choose BD is equal to 0. We have to choose it some way such that this determinant condition is satisfied. You also find that in linear system theory totally without MPC, okay? We didn't discuss it in the Regelsysteme 1 because we kind of assumed the system is stable, okay? We said it has no zeros at the origin and so on. We neglected various conditions that we mentioned when we set the no offset property. We kind of sloppily discussed that, okay? Those are conditions that also have to be satisfied in the linear case for using an integrator in order to produce no offset. So this is a not special condition. They just come out here in a very precise linear systems framework. That's it regarding no offset. So if you want to do no offset, you have to introduce the observer with a special structure that you estimate the disturbance. You then add those target equations to the MPC formulation, and that formulation will give you no offset. There's some restrictions, number of disturbances, number of outputs, number of inputs, etc., that are all covered by the theory that I'm not dwelling on in detail now, but that's the concept. And in general, if you select as many disturbances as you want outputs to be controlled without offset, it's okay. Okay, any questions on this? But it's an important application topic. Okay. This was a long-standing issue, and people did not understand why they had why they had offset, etc. So it took a while to derive in the literature to derive those conditions. So it's not a trivial thing, but this is now all finalized. This is the theory, and here you really need that theory to do the correct formulation of the problem in practice. So this is theory needed for doing the practical problem. Okay, there are no questions, then we move on to the next topic. Okay. Next topic is soft constraints. What's the motivation? And I said that already at the end of Professor Borelli's lecture. In general, you have two types of constraints. One constraint is that the inputs, the manipulated variables. So what are those? I mentioned those are, for example, valves in some pipe that can go from completely open to completely closed. That is some voltage supply to some motor that has some maximum possible voltage that you can apply to between 0 and the maximum voltage. So you cannot go higher without destroying it. You cannot open the valve once it's open. So those are hard constraints. Okay, there's no little bit more, a little bit less. Those are hard. The input constraints are usually hard. Okay, the output constraints also exist, but they're usually not hard. There's some maximum pressure, but yeah, as long as you're not too long in the maximum pressure, it's okay. Okay, and you can violate it a little bit. But not too much. Okay, so those quantities in terms of the pressure, or you may also have some current limitation. Okay, is there a hard limit? No, you get a little bit higher current is okay. Okay, and so you have on those output or state constraints. Usually, they are not hard. Okay, they're not hard because you cannot guarantee it anyway. Even with whatever control system, that they are satisfied exactly. You don't know the model exactly, so you don't know exactly what's allowed as an input to keep that output within constraints. So, as it says here, the output constraints are really hard. Furthermore, the output constraints lead to a lot of complications in the controller design. Okay, they lead to all those sets that Professor Borelli introduced. They are essential to understand the range within the controller can operate, which are all obviously depending on model knowledge. So output constraints make your job very hard in terms of the theory. And then you say, especially in this, you say, okay, why make my life so hard if the output constraints aren't hard in reality anyway? Okay? And therefore, in industry, most application don't put in hard output constraints. They put in soft output constraints. The other problem is there's no way, say in output constraints, let's say the pressure for some reason, something failed, etc., exceeded your limit. Okay? You cannot have a controller that says, pressure exceeded limit, don't know what to do. Therefore, you need a patch. So you need a patch that, okay, if the pressure exceeds the limit, then do this and this to get it back into the limit. So then you have to patch up your MPC controller, which you have designed very carefully, to deal with those abnormal situations that the pressure went outside the limit, how to get it back into the limit. That's not very practical, okay? So you need to have one controller MPC, then patch it for this situation, then patch it for this situation, etc. So that's another disadvantage of hard constraints. You cannot guarantee that you will never go outside. With a valve, you know it's not going to go beyond this range. Okay? But it can go, an output, a pressure or something can exceed the range, and so you want to soften those constraints. So how do we do that? What's the mathematical formulation? And there's just a little trick to keep in mind. And that's why we do this whole discussion. Not something very complicated, simpler than the no offset case we discussed before. So this we say, okay, this is our problem, very simple, and for the moment we'll just say g of z is a scalar, so we have one constraint, g of z, we have this optimization, f of z, that we do, and we have to satisfy a constraint, g of z less than 0. Now, how do we soften this constraint? Now, this is a strict inequality constraint. That's something like pressure less or equal to 0 fixed, okay, not less than 0. Not larger than 0. Not allowed to be larger than 0. Hard bound at 0. Okay. Now, how do we soften it? We change that and say, okay, g of c less than epsilon. Epsilon is some small positive number. We allow it to go a little bit beyond it. How do we choose that number? We don't choose it. Okay. We put it as a penalty on the objective. So L of epsilon is a penalty on epsilon. So when I now minimize over z and epsilon, what will it do? It will try to drive the epsilon, if that L of epsilon is positive, it will try to drive the L epsilon to 0. Okay? So it will make the L epsilon small, so it will make epsilon small, and therefore it will drive the constraint as close as possible to 0. That's the idea. So instead of a hard constraint, we relax the constraint, as we say it, relax constraint, okay, by epsilon. And we don't choose the epsilon fixed, but we choose it through the optimization. And by choosing the L of epsilon, we will tend to drive it to 0. So the more I penalize it with L epsilon, the smaller that epsilon will eventually become. So it may violate a little bit, it may violate a lot, but when the L epsilon penalizes it, so it will tend to drive it to 0. We'll continue. Okay, it's not maybe 15 minutes. So that's the setup. Okay, so the question is now, how do I choose my L epsilon? I have a penalty term that penalizes epsilon positive. Okay, penalize violation of the constraint, but how do I choose it? And one requirement that I think makes sense that we want to set ourselves, this requirement on L epsilon, is that this should violate the constraints, meaning epsilon should be positive, only if it cannot do otherwise. Okay? So if there is a feasible feasible z within that range g of z less than 0, okay, if there's a feasible, it should find it. Okay? It should not violate the constraints just because I now formulated a different problem. Only if there's no z, okay, that satisfies that constraints, then it should look at violating it, and as little as possible. So that's my requirement on how to choose L epsilon. And the kind of obvious thing that you would say, okay, well, how about L epsilon is equal to epsilon squared? Okay. That would penalize my epsilon. Okay, it would be large, would drive it back. But it turns out that's usually a bad choice. Why? Because it turns out, as it's stated at the bottom here, it could be that then you get an epsilon greater than 0, meaning violation of the constraint, even though a violation is not necessary. And the idea is simple, and let me illustrate it to you. So that's a very simple example, but obviously it's general. So we have a very simple constraint, so that constraint just says z minus z star less than 0. So that means z is z is less than z star. So it means that's my feasible region. That's my feasible region, this shaded region. I'm only allowed to be in that region here. So we know where the optimum is. The optimum is clearly here, okay? That's the smallest f within the feasible region. Now what happens if we relax the constraint? So we don't say this is 0, but we say less than epsilon. And we choose a penalty term as said here, a quadratic penalty as I suggested, v times epsilon squared. So this is my red curve L epsilon here. So it's 0 here, no penalty. But then L epsilon is quadratic as indicated by the red curve. So what is now my new optimization problem? By new optimization problem, I minimize the unconstrained problem, minimize, oops, okay, my unconstrained problem this is what I minimize. Objective plus penalty. How does this look like? That's the sum of the red and black curve, and that sum gives you the green curve. Where is the minimum now of the combined problem, objective plus penalty? It is here. It is not here where I want it. Okay? It is here, and actually at the minimum, it violates my constraint. Okay? Because I'm not in the gray region. I'm in the white region. And you could say, okay, I have chosen v epsilon squared. How about if I make v larger? Okay, if you make v larger, then this will go look something like this, and the optimum will shift here. But it will never go here, regardless of how large you can choose v. So it means in order to make sure that you don't violate the constraints if you don't have them, you would have to run v infinity. For any finite v, this penalty does not give you the correctly constrained solution, even though you can obtain it. So this is a bad way of choosing the penalty function. What we want to do, we want to have a green curve that eventually, and I will put on my green color here, I want a green curve that looks like this, okay? Because if it looks like this, it will go back to the true minimum. And that's what I can get if I choose a linear penalty function. A u times epsilon, not u times epsilon squared, u times epsilon. This is now my u times epsilon, my linear function. The green here is now the sum, and you should see trivially that where's the minimum? It's exactly where it should be, where the constraint minimum should be. I just want to make sure that it is here indeed the minimum, okay? Because it could also be, if I turn on now a different color, this yellow color here, it could be that if I don't choose u big enough, that actually it looks like this, okay? It looks like this, then it will not be the minimum. So I need to choose it big enough such that I get a minimum here. Okay, so I need to choose my u big enough. I need to make it steep enough. So obviously how steep depends exactly on the slope of the function at this point. And this, in this special case, is this slope condition down here. So there's some minimum u that will give me the correct minimum. But it's not infinite, it's some finite number. It actually has to do with the slope of the little function. So you can think about those slope arguments as a simple example, but what's the result, the final result? That the penalty function u times epsilon satisfy the requirement for any u greater than u star, where u star is the optimal Lagrange multiplier associated with that constraints for the original problem. So there's some finite value, it's actually defined, it's related, and you can think about it in terms of the optimization that you learned on day 3. It's related to Lagrange multiplier. So that's the way to do the penalty. The penalty is to do this here. The only disadvantage for some computations of this penalty function, it has this kink, as you saw. It has a corner down there. And for optimization and for software, you usually don't like those corners, okay? You don't like the non-differentiability of this function. Note it here, okay? You have this non-differentiable corner. Easy to fix. All you do is you add an additional term, v times epsilon squared, which smoothes the kink. It doesn't matter how big v is, it smooths it. But it still has those u epsilon characteristic. It just doesn't have a zero slope. So you will still have the properties preserved exactly that you want, but smoothly. How do we do with multiple constraints? We can do the same thing. We just take u times ej, that was our linear penalty term. We sum all those over the different constraints. For each constraint, we get a different epsilon. For each constraint, we choose a different u, and you sum those penalties, and this gives you the L epsilon. And by choosing the u, you can penalize the violations differently. So you can say, okay, this is a very important constraint, so I choose the u large, so that if possible, it will keep it. If it has to be violated, it's less violated than something else, etc. So we can play with the uj to weight the violations so that they're violated, and you can even do it. There's some weighting procedure. You can even weight it such a violated in sequence. You can even choose weights and say, first this constraint is violated. If this is not enough, then this constraint is violated, etc. And you can go through the whole sequence to in terms of the violations if necessary. Okay. Are there any questions on that? So that again is something very practical. Okay. They've given you some theoretical foundation of how to choose third penalty, but this is what you do standard in industrial MPC algorithm. Because you don't want to deal with the situation, I'm outside the constraint, what should I do now? Okay, you don't want to have a controller like this. This doesn't happen once you soften the controller in this way, and it will tend to bring you back into the unconstrained region. As part of the algorithm, not as part of a patch you put on top of the algorithm. Okay, if there are no questions here, we go to the last problem. Very simple, only I think 2 slides. Just says generalization. Because you find that in the literature, you find it in industrial algorithm. So what's the generalization? No big deal. Instead of having one constraint, one horizon n, remember we had this one horizon n, say, okay, I choose different horizons for different parts. So for example, I will choose one horizon for my outputs, that's the horizon ny. Okay, so I add up those terms only up to ny. I have a different horizon for my controls, nu. Okay, nu. So this controller is between some u min and u max, but only over some horizon nu. You can make the constraints on the outputs, like here, time varying, and several of you asked me earlier today, etc., can the constraints be time varying? Yes, they can be time varying. This is indicated by that k here, the maximum minimum can be time varying. Obviously, some things you have to obey for this to make sense. For example, you don't want the control to continue and not look at the output, so the horizon nu has to be less than the horizon ny. Then NC is, I don't know what's happening here. NC is the place where you want to look at your constraints. So the constraints, you don't look at it all the way to the end. You look at it over some constraint horizon in C. So there are a lot of fiddling parameters that you find in industrial algorithm. I don't like them. Why do I not like them? You have all these degrees of freedom. You have no way what to do with them. Okay, you have now more knobs, and how can you trade off the different knobs to do what you want? Very difficult. So you get this difficulty of the choice that is very difficult to do correctly, and moreover, those modifications to the algorithm, all the ones that I mentioned, all those guarantees with those are all lost. There's no theorem for any of those. Okay, so you're totally in the dark on how to choose them, etc. So this is not what I would recommend to do. You know, just to have more choice doesn't mean it's better, because you don't know how to take advantage of those choices. On the other hand, there's the other modifications that I just mentioned here, and that's called move blocking. And what move blocking does is, if I look at my t, and if I look at my manipulated variables u, and let's say those are the time intervals, okay, then the move blocking says, okay, after time interval 4 here, I don't need to determine the u's so accurately. I will just assume that after u, let's say, I do that over two steps I have the same u, and then afterwards I can change it, and then from there to end of the horizon I use the same u. Okay. And this makes sense because you reduce the degrees of freedom. So as I said here, you have the first, so instead of having maybe 10 degrees of freedom, you have one, I don't know what's happening here. So instead of the 1, 2, 3, 4, that's u, then you have 5, and here 6. So instead of saying 10 degrees of freedom, you have just 6 degrees of freedom. You simplify your optimization problem. And the nice thing for this type of strategy, actually, there are some rules on how to choose that move blocking such that the stability and feasibility conditions are preserved. So with this move blocking, you can preserve the stability results. Not arbitrary move blocking, but somewhat restricted move blocking, but you can do that and preserve the stability results, and that is useful. Okay, so if you want to simplify the optimization problem to solve, this is the way to do it. This here, not so great, because you don't know how to choose all those parameters, and all your theory is destroyed. That's it for now. So we have no offset. We have softening the constraints, inherently, imminently practical, and we have those simplifications that are often done. And here the recommendation is just to do the move blocking and not the other tricks. Okay, so have a good, we'll see what we do with this lecture. Have a good afternoon, and I'll see you tomorrow. Tomorrow we'll have all the industrial lectures starting at the usual time.